Good evening, everyone. I'm Priya Natarajan. I'm the current director of the Franke program in Science and the Humanities. And I'm an astrophysicist by training, and I'm a faculty member at Yale's Departments of Physics and the Department of Astronomy. So I am delighted to welcome you all to this evening's talk, which is part of our ongoing thematic workshop and study on the nature of inference, understanding the nature of inference, in particular, understanding causation, correlation, and understanding these issues from a multidisciplinary viewpoint. So as many of you know, we've had these monthly seminars. We've had experts, pioneers who have been working on using machine learning and artificial intelligence methodologies in their particular disciplines, ranging from chemistry, biology, computer science, and physics today. And I am really happy to introduce today's speaker, who's part of our core team for this project as well. And today's speaker is Professor Kyle Cranmer, who is currently at NYU. But before I give you an introduction to Kyle and his work, I want to say a big thank you to our benefactors, Richard and Barbara Franke, who I think are amongst the audience today. Their generosity and support of all the interdisciplinary activities at Yale, multifarious activities and centers that they support, including the Franke program in Science and the Humanities, has been very, very impactful in getting scholars who are otherwise in silos to actually collaborate, talk, and interact with each other. So let me go on now to tell you a little bit more about our wonderful speaker. Kyle is currently a professor of physics and data science at NYU, and he's a visiting scientist at Meta. In July, he will become the director for the American Family Insurance Data Science Institute at the University of Wisconsin-Madison. It's their brand new effort in data science at Madison. He obtained his PhD in physics from the University of Wisconsin, so he's going back home in a way in 2005, and he got his BA in mathematics and physics from Rice University. He's a recipient of many awards. I'll just list a few. He was awarded the Presidential Early Career Award for Science and Engineering, the PCAS in 2007, the National Science Foundation's Career Award in 2009, and he became a fellow of the American Physical Society for his work on the Large Hadron Collider. So one of the key sort of the seminal contributions that Kyle has made is the development of a framework, a very robust framework that enables collaborative statistical modeling. And as you can imagine, with the vast amount of data from the Large Hadron Collider, his work was used extensively for the discovery of the Higgs boson, which, as you all know, was a major breakthrough in particle physics announced in 2012 at CERN. So his current interests are at the intersection of physics, statistics, and machine learning. And as you can probably guess, he's one of the pioneers in our field, trying to leverage these new innovative methods for obtaining a deeper understanding of the physical world. So before I turn it over to him, let me very quickly remind you that the format of these talks, please feel free to put your questions in the chat. If you have a burning question, do raise your hand, something that requires immediate clarification. Otherwise, we prefer to have the Q&A session after the talk. And as you all know, the format of these talks has been, we first start out with a colloquium, and so which Kyle will be giving, followed by a few days later, an actual sort of discussion session in which we have an interlocutor, another expert in the field who approaches things from a slightly different vantage point, engaging with Kyle's talk today, as well as offering us their own insights. And so we are delighted to have Dr. Zena Tavares, who's at Columbia, who is also here in the audience today, who will be leading the discussion session and framing some of the open questions and engaging with the material that Kyle will be presenting today. And these sessions have been wonderful, lively discussions, and really look forward to it. So Zena and Kyle will be in conversation next Wednesday, at 4 p.m. And to quickly give you a preview of coming attractions, we have Carl Zimmer, who will be speaking as part of the Distinguished Speaker Series about his new book, Life's Edge. And that's at the end of March 30th. And then we have our Mapping as Knowing lecture series continuing with Victor Coelho in April. And we have a bunch of our own Frankie Fellows speaking later on in April. Anyway, without further ado, let me now turn it over to Kyle. Kyle, we are delighted. I wish we could have hosted you in person, both Kyle and Zena, but things are as they are. I think we're just really grateful and deeply appreciative of you agreeing to speak to us on Zoom. Thank you.
Thank you very much, Priya, for the warm introduction, and thank you, Zena, for agreeing to the conversation next week. I'm really looking forward to it. Let me share my screen here. Hopefully this is fine. Okay, does that look good?
Yep, looks great.
Great. I'm gonna hide you so I can see a little bit better. Okay, so yeah, I'm really excited to be invited in this series. It's been really interesting. I've been able to watch quite a few of the talks, not all of them, but I think most of them, as well as the discussions and conversations that followed, which I find to be really interesting. I like the format a lot. So thank you very much for having me. I think I'm maybe the last one of this particular slate, but maybe there'll be added some more. So I tried to take on a little bit of a role of referring back to some of the other talks that happened in the series. And so the title I chose is Causality at the Intersection of Simulation, Inference, Science, and Learning, and hopefully be able to see how all these get tied together. So I'm going to start by saying that there were a few of the talks that happened earlier where causality was being, examined, and that word was being used in a particular way that physicists use it, which has to do, for instance, with things like the arrow of time, the structure of space-time. That's my little diagram here. That's sort of this is some event. Whoops, excuse me. Some event, and you have a future light cone and a past light cone. And the notion of two events being maybe separated so that they're out of causal contact with each other, and other points that are in causal contact with each other, trying to understand that in the context of like I mentioned before, the arrow of time, or in the context of quantum mechanics, et cetera. And these were very interesting talks. But there were some other talks that were a slightly different usage of the word causation, which is more in the language of sort of causal inference, and kind of from the statistical point of view. So there you have things like, here's my little picture of a sun, and the sun, is leading to hot, sunny weather, which kind of causes people eating ice cream and sunburns. And then that gives rise to some kind of correlation between ice cream and sunburns, but we would probably all agree to say it's wrong to say that ice cream causes sunburns. And so that's the typical correlation does not cause, correlation causation aren't the same thing. And so the mathematical framework for trying to think about this and causal reasoning were sort of the subject of for instance, these two talks. Now, after the talk by Janan Ismail, James Woodward was the conversant that followed up, and I grabbed a little bit of the transcript from their conversation because I found it to be very interesting, and it's kind of a nice entry point into what I wanted to talk about today. So James was pointing out, in response to the talk, that there were potentially some interesting route to be had on the philosophical side by thinking about what he talked about, a component that has a more normative character, talked about the procedures that make causal reasoning or learning causal relationships from certain kinds of data reliable. And he said that the sort of normative aspects of things, when you do that, then you bring in the connection with statistics, causal reasoning, machine learning, and AI, and that it would be interesting to sort of see how these two ways of going about the general topic relate to each other. And so I'm going to definitely sort of follow up from that a little bit. So while I am, my core discipline as a physicist, I've been doing a lot of work on machine learning and AI, and a lot of what I have to say kind of comes more on the statistics side of things, but they're of course very deeply related. And so to try to kind of prime that, I'm going to just give a few graphic examples. So here's a system, It's a toy that I have on my desk right now. And when you see this kind of thing, you see the balls bouncing around, it sort of naturally, draws to mind a probabilistic description of what's going on. And of course, thinking about these kinds of things, are really back in the early history of our statistics and probability. But if you think about the system as it evolves, when you describe it, it's natural to think of the balls bouncing either to the left or to the right with some probability. And so you have this probabilistic description where the system evolves in a stochastic way. And now the same system, if you look at it, more closely and in slow motion, you see the balls bouncing around. And now you're thinking maybe more like classical mechanics of a deterministic evolution of a system where the balls are bouncing through this lattice of pins. And if you knew the initial state perfectly, it would unfold in a totally deterministic way. And so that kind of points to this other notion of causation that's more from the physicist's point of view and things like the arrow of time and et cetera. Now, if you want to try to sort of reconcile these two different ways of looking at the same system, we know that this is very, sensitive to the initial conditions. And if you slightly perturb the balls at the very beginning, they would take a different path through the lattice of pins. And so each realization of, turning this desk toy over gives you effectively some, random outcome. Now, this also happens when you, for instance, look at, climate science. These are simulations that are going on of eddies inside of the oceans. The description of this is, fluid mechanics. So you have things like Navier-Stokes equations, again, that are deterministic. There is some scale at which you can't resolve what's going on anymore. And so you have this kind of chaotic behavior. And so there is a connection again to, randomness and stochasticity. But it's kind of interesting here, the higher level picture is kind of looks like deterministic. And then, but then you have some lower level information that you can't resolve. So that introduces some randomness into the system. And then you have, you have different arrangements of this. And I guess there's just the observation that as you sort of, step through, step down the reductionist ladder or, maybe step up the ladder of emergent phenomena, that you often see switches in whether or not the kind of effective description that you're working with looks stochastic or deterministic. And I think that's just kind of an interesting observation. So for instance, when you're talking about thermodynamics or thermostatics, you have, pressure and volume and these kinds of quantities. And there are equations that relate them, and it looks much more deterministic. But we, then understand thermodynamics is arising from an underlying statistical mechanical description of what's going on. And then here, kind of flipping the roles around, this is supposed to be the Twoslit experiment. And at the top, you see, for instance, electrons hitting some screen or something like that. And the individual electrons are like point-like particles, and they have a random nature that's associated with the kind of randomness of quantum mechanics. But at the same time, we think of a kind of underlying deterministic evolution of the wave function, due to Schrodinger's equation. So this is just basically to prime that the two different ways of thinking about causality and deterministic systems and stochastic systems are, very closely related. I'm going to be talking more about stochastic systems, but just keep in mind that this relationship. Now, in the conversation that I alluded to before, later on, about a half an hour into the discussion, James pointed out again that this important topic called scale separation, which is essentially the observation that if you wanted to describe a bulldozer, you don't need to bring in quantum mechanics or quantum chromodynamics to try to describe that. And he says, you could imagine an alternative world where to basically model anything, you have to, model all the way down to the most detailed way, but that doesn't seem to be like how our world is arranged, and that we often see some kind of approximate decoupling between the different scales, and that facilitates causal reasoning in our world. And I 100% agree with that, and I'm going to sort of show some examples of that. So now moving on to the kind of the topic of this series is inference, and of course it's related to causation and correlation. And so the way that I'm going to be talking about it is that in the context of some scientific theory, for instance, as a particle physicist, we have theories And those theories often have some parameters that call those theta. And then I can use that theory to make predictions about what I will see in a particular experiment. And so I'm making predictions about the data, which I call X here. And the process of inference is sort of the inverse of that. From some data, I would like to infer something about the theory that's in question. And that can be done in various different ways. Often it's phrased in the context of Bayesian inference, where if you want to say something about probabilistic about a theory given some data, via Bayes' theorem, you can relate that to a statement about the probability of the data given the theory. So this is what's called the likelihood function, and then times a prior probability for the theory. Now, in particle physics, I'll just make a quick comment that the prior probability for the theory is a very thorny thing. It's not like, what's the prior probability that you have the flu or something before you have COVID before you take a COVID test. Here you're talking about does some fundamental particle exist in the universe or not? And it's hard to talk about that in a probabilistic way other than through more like subjective notions of belief. But this term, the likelihood function, is sort of very well grounded in how we as physicists, take a theory and turn that into predictions about what we expect the data to look like. And I'm not going to get into the issues of Bayesian versus frequentist statistics, really, other than just to point out it's an issue. The main thing I'm going to be focusing on here is the details and difficulties with the probability of the data given the theory or the likelihood function. And so I'll come back to that later, but this is sort of roughly the probabilistic way in which I'll be discussing inference. Now, this is a picture of an actual collision that happened in 2012 and on the 10th of June at the Large Hadron Collider and the ATLAS experiment that I work on. And obviously it's a computer, rendering of an actual collision that happened in the data. I'll talk about it a little bit in some more detail in a moment. This was one of approximately a quadrillion collisions at the Large Hadron Collider that happened in those couple of years. So there were many collisions like this, but this one was one that was particularly important because it was a candidate for being consistent with the production of the Higgs boson. So we had more collisions that were like that, and we did some statistical analysis of the data, which I'll say a little bit more about. And that's what led to the claim of the discovery in July of 2012. And one of the things that's interesting about this is this really within about a week of that was one of the kind of breakthrough milestone papers in deep learning. And that's when we really started seeing deep learning as we think of it today in the context of image analysis, image classification, really starting to work quite well. And very shortly after this, you started getting situations where deep neural networks were sort of claims of superhuman performance and things like this. So this was definitely a milestone moment, both from the point of view of deep learning and from particle physics. And for me personally, right after this, I went on sabbatical, and that's kind of I really shifted my focus to thinking about how to put these two together. How can we take advantage of what's going on in machine learning and deep learning for the purposes of doing science, and what does that relationship look like? And this was interesting because it's kind of the backdrop of a debate that's happening across all the sciences, where you see a pendulum swinging essentially from, in the context of physics, you had traditional approaches to analyzing the data where you have more handcrafted types of data analysis, largely guided by expert knowledge and theoretical insight, switching over to something that's really started, even a decade or more before with the rise of big data and data science and deep learning. And there's a push to be ever more data-driven in the context of machine learning. You use this phrase end-to-end learning, and that basically is hinting at sort of eschewing expert knowledge and what sometimes referred to as hand-designed features and things like this, and really try to have an end-to-end system driven by with some deep neural network or something in the middle that tries to go from the data directly to solving your problem. So that would be something like data from the LHC to, yes, you discovered the Higgs or not, like in one step. And so that's a very different approach. And this is paired with a kind of desire that maybe AI is somehow like magical and it's just going to look at all the data and figure things out. And it's, again, paired with a discussion that started really with big data about these kinds of, I would say, somewhat ridiculous claims that that we're looking at the end of theory and that the data deluge makes the scientific method obsolete. Quotes like this, that all models are wrong and increasingly you can succeed without them. And given everything that's going on, it's hard to just dismiss these claims because something is happening, but so that's partially what we want to look into a little bit more deeply is to what degree is this, are we witnessing some kind of radical change in the scientific method, and what does that look like? So I'm going to switch now to kind of contrast what I was just saying on the big data side go back to the more traditional approach, and then start to bring in elements of causation. And I'll also say that while physicists are very comfortable with talking about causation in the sense of space and time and these kinds of things, oftentimes we are not particularly well trained in the language of causal inference and things like this. It's actually something that's very core, for instance, in the social sciences and medical sciences and sometimes in particle physics or other areas of physics. The causal relationship is so obvious that it's not really something that you needed to develop a sort of calculus to understand. And so in that way, we're sort of playing catch up. But at the same time, a lot of the success of physicists has been based on leveraging causality, notions of causality. And so that's a kind of interesting thing to try to reconcile. It's partially what I'm thinking about a lot these days. So this is a picture with me and Yuta Pearl, who wrote this book of why. And one of the, in his book and in his writings, he talks about what he calls the ladder of causation. And he's saying the lowest rung of the ladder is association. So that's really at the level of like correlations. And so what you see is sort of seeing and observing where you just have data, basically. And the point here is that there are a set of questions that you can address when you have a lot of data, but there are other types of questions that you cannot address just with data. So the idea that the big data is going to solve all your problems is really only restricted to this lowest rung on the ladder. And in fact, there are higher level questions where you want to ask questions like, what would happen if I do the following? If you intervene on the system, and those kinds of questions cannot be answered just through data alone. They really require essentially some other kind of structure that you add to it, usually in the form of some kind of assumption. And I will give a concrete example in just a moment. But before doing so, I'll just say that there's even a higher level of question, which are referred to as counterfactuals, where you're imagining and you're sort of answering questions like, what would have happened if I had done the following? And so that's interesting because you're sort of conditioning on things that actually happen. So you kind of in principle can't answer that question because it already happened. While in the context of interventions, you could make the interventions and actually see what happens, right? So these are the three levels, and they do have a very grounded formal mathematical basis, which I'm not going to go into, but just to say that they're not squishy concepts. They're really very formalized, well-defined concepts. So let me give a concrete example. This is here you see some code. So there's three very short little computer programs where you have random variables X and Y, and here you also have a random variable Z. And then there's a little drawing associated to it. So here the story is that the random variable X was first, and then it sort of causes Y. And you see in the program, X was generated through the random number generator first, and then Y depends on X. So this is the direction of causation. Here you see the opposite. Y is generated first, and then X is generated, and it's a function of Y. And then finally, you have a different situation where Z, which is not, Z is some third variable that's generated, and then Y and X both depend on Z. Okay, fine. So, and here's the little drawing associated to that. Now, why is this interesting? The reason that this is interesting is there's three different stories about how the data came to be, the data generating process, but all three of them give you exactly the same joint distribution, or the correlations between X and Y are exactly the same in these three different stories. So in that sense, if you just had data, you wouldn't be able to answer which of these three is responsible for producing the data. But if you can do interventions, if you can go in there and like poke inside the system and, for instance, set the variable x to be a particular value, and that's the notation here is do x. The do operator means you're going and intervening. And if it was a simulator, what you would do is you just, at every step of the program, you just make sure x is equal to 3. So you just see extra lines stuck in there where you force x to be 3. And if you do that, then if you look at the data that comes out of this thing, x will be 3, no surprise there, but the distribution of y will be different in these different cases. And so that points to the fact that if you can do interventions, you can answer a richer set of questions than you can if you look at just data alone. Okay, so you need to be able to make those kinds of interventions. And I'll come back to that later. Okay, so that is all a little bit of a preamble. And now I'm going to switch to a topic which is sort of near and dear to my heart, which I refer to as simulation-based imprints. So I'm going to try to sort of set it up broadly, give a feel for why it's important, and tie it back to some specific examples in physics, and then later we'll go back to kind of science and machine learning and causation and things like that. Okay, so the first slide in this section starts with the observation that science is replete with high fidelity simulations. Okay, so we have simulators for our particle colliders at the Large Hadron Collider. We have simulations for neuronal activity. We have simulations for how epidemics spread. We have simulations for gravitational lensing and the evolution of the universe on the largest scales. We have simulators for how air moves around an airplane, which we use to design airplanes, and simulations for how proteins will fold and things like that, which helps us in the design of drugs and et cetera. And these simulators, what's interesting about them is not only can you use them to generate synthetic data, they are causal models for how the data generating process, They actually have some mechanism of what you think is happening, right? So in the case of proteins, you have atoms and molecules, and they're maybe surrounded by water bumping into them, and you have energy, for some arrangement, and the system evolves in a certain way. For epidemics, you have individual people maybe that you're modeling, and they may get sick or not with some probability, and that system evolves in some way. And so you can imagine in that simulator, for instance, intervening, like what happened if I held on to the protein and pulled it in a certain way, what would happen? Or in epidemics, you could do a simulation of what would happen if everyone got a vaccine, for instance. So the fact that they're causal is very important. And now, as you'll see throughout the talk, there's a kind of computational, bent to a lot of the way that I'm thinking about things. And so it's important to recognize that the expressiveness of programming languages and the modern computing and all of this allows us to really scale this up and actually simulate these very complicated systems and make some very high fidelity simulations. And that's something that's a capability we didn't have 50 years ago. And so this is definitely changing the way that we do science. But as you'll see in a second, it's a little bit out of step with the way that we approach statistics currently. And so that's the point here, basically, is that unfortunately, these simulators, while they produce very high fidelity simulated data, are poorly suited for statistical inference. And so why is that? Well, let me try to give you some feel for why that is. So before doing that, I'm just going to lay out a little bit of notation. So I talked earlier about on the left side here, I have basically the theory. It has some parameters, which I'm calling theta. And those might be, for instance, in the case of COVID or something, it might be like, how virulent is this new virus? How quickly does it double as it goes through the population? Or it could be a parameter like the cosmological constant of the universe or the mass of the Higgs boson, what have you. So you have these kinds of parameters over here. And then the simulator allows you to make predictions for the observed data. It's not going to just be, the observed data is not going to have a particular value. It's going to have many possible values. So it's going to describe a probability distribution over the observed data. But inside the simulation, there might also be other random variables that are referred to as latent variables, which are part of the story of how the data came to be, even though you might not be able to actually observe them in your experiment. So I'll give some examples, but you could imagine that, for instance, in the case of COVID, X might just be like hospitalization rates or something like that, or people, testing, how many people tested positive with COVID. The latent variable would be something like how many people actually have COVID. You don't know that, but if you're doing a simulation, you would have access to that variable. All right, right. So, so then the question of this inverse problem or of inference is to go from the data X to, say, the parameters of interest theta. Now, here's that same desk toy. Now, I'm just going to, I don't know if you can see it, here's the actual toy. You can imagine I want to introduce some notion of a parameter. So let's say I tilt the toy to the left, or I tilt the toy to the right. If I tilt it one way, it's going to bias the distribution so that it doesn't look the same. So imagine that I want to try to infer this parameter theta, which is, say, like how tilted the whole toy is. I could relate that maybe with the probability that a ball bounces to the right. And so that's the thing that I want to infer. And I'm going to do that based on the distribution of where the balls land at the bottom. And I'm going to call the location where they land at the bottom X. And then the latent variable would be the path that the balls took through this lattice of nails. Okay, and in principle, I could maybe go observe that, but I wasn't paying any attention. It was too fast. So really all I get to observe is where they landed. And I'm going to think of the path that they took as the latent variable. So if you want to predict what is that distribution, well, you might say, okay, well, I can do that. It's either going to bounce to the left or to the right with some probability. There's many possible paths, but there's some nice symmetry that's there. And if you took your combinatorics class, then you can figure out what that distribution should look like. And there it is at the bottom. It's the binomial distribution. Okay, so you would assume this is the binomial distribution, as I did once before teaching a class on this subject to undergraduates. But then I compared that to what it actually looks like, and it doesn't match up. And then I was a little confused as to why. And then I took the slow motion video that I showed you before. And if you look closely, you'll see that the balls are not just going left and right. They're bouncing all over the place. Sometimes they skip over 2 or 3 pins. They run into each other. It's a lot more complicated, right? So if you wanted to say, what's the distribution here down at the bottom, I have no idea what that distribution is, but I can simulate it. And that's kind of, part of the point. So here's an example of a simulation for this exact thing done by my colleague, Gunjus Biden. It looks very realistic. It looks a lot like that video I just showed you. You don't know exactly how bouncy the balls are, how big the nails, the pins are, et cetera, but you can simulate it. And symbolically, if you ask yourself, what's the probability distribution that the data, of the data landing in these different bins at the bottom, given the parameter that says like how tilted it is, symbolically, it's equal to, don't be worried about the math too much. This integral just means I'm going to sum over all the possible trajectories that the balls could take that would give you that same observation. The problem now is that I can't do that sum with nice mathematical tricks of combinatorics because there's no nice structure anymore to take advantage of. And this latent space of different possibilities is growing very, very rapidly. And so that means that basically this integral that I want to perform, where I sum over all the different paths, is now intractable. And that means that the likelihood, the thing that relates to the probability of the data given the parameters, is not available to me anymore in any practical sense. And so here I would say that the likelihood is intractable. And that means that basically all of the different approaches for doing statistical inference require that you have the likelihood. And so what do you do now, basically? So while the likelihood is intractable, I can still generate synthetic observations with my simulator. And so it seems like you should be able to make some kind of progress by basically comparing the outcome of the simulations to the actual data. And so then the question is just how are you going to do that in practice? So let me go back to the Large Hadron Collider and tell the same story, but with a more complicated real world science experiment. So here's the very complicated data at the Large Hadron Collider. It's very high dimensional. The detector has about 100,000 sensors on it. And so when I want to make a prediction of what will happen, I start off with a theory, which is, based on quantum mechanics and quantum field theory that we call the standard model. It has some parameters. I can then use that theory. I don't know, maybe you've seen things like Feynman diagrams, sort of pictorial representations that allow me to calculate what would happen, what's the probability that the particles are going to scatter off of each other in a certain way and that this interaction will take place. This interaction has a Higgs boson in it that decays into some other particles called Z's that decay into other things. Doesn't really matter, but these particles over here on the right are coming flying out into the detector. The problem is that we don't see those directly. Instead, there's another process where they radiate and it becomes really messy. And at this stage, I can't write down what's going on, like really on a pencil and paper. I can describe what happens kind of locally every time you see one of these splittings. I can write down a probability, but the whole process is this very complicated, thing. And so I can put it on a computer, but it's very difficult to work with a pencil and paper. So you go from the latent variables that were associated with this first stage, followed by latent variables, random variables that I don't get to observe, followed with this complicated showering process is what it's called. Then these particles are physical particles that come flying and smash into our detectors, and they ionize and they run into pieces of metal, and they do all the things that they do. And then there are literally hundreds of millions of latent variables associated with how these particles interact with our gargantuan detectors. And finally, you get observed electronic signals in our detector, which is like the raw data that is collected by these experiments. And so that's X. And so if I want to think about how do I simulate that, I just told you the physical story. There's actually software for each one of these stages. And you can think of these different programs as basically encoding these probability distributions that go from one step to the next step to the next step. And it's really kind of hopping, from the smallest scales to the next scale to the next scale in some probabilistic way until you get to the final observations. And we call these Monte Carlo generators. And that's because Monte Carlo is a technique that you can see as a way of trying to integrate these random variables. So symbolically, you could write down the simulation this way. You're saying basically the likelihood of the observations given the data is equal to this integral of this, this product of probabilities. But this integral is like 100 million dimensional, and there's no way that you're going to do that, basically. Like this is a totally intractable integral in practice. So that means that the likelihood is intractable here. So what do you do? Like, how is it that we discovered the Higgs boson if we're in this kind of setting, right? So what we have done as a field for decades, and other fields have kind of developed their own version of this, ranging from genomics to cosmology to all over the place, is that you use your kind of domain knowledge, your expert knowledge, to think about like, well, what is it about the data that's going to be useful for testing the hypothesis that I have in mind? And that turns into basically, in the context of the particle physics, taking very high dimensional data from the detector and then distilling 100 million electronic sensor readouts into just one number, which is the horizontal axis in this plot, which I'm going to then make a histogram of. And I'm going to histogram the data. So every collision, I have just one number, and I have many collisions. So I build a histogram, and that's like the black dots in the histogram. And the red histogram is basically what I predict from my theory. And the important part is that I can sort of fill that histogram up with a bunch of simulations. So if I step back and like look at the text on the slide here, in a statistical language, you would say this one variable that distills all the information from this high dimensional data is called a summary statistic. That's what a statistician would call it. Sometimes it's related to feature engineering, is what a machine learning person might call it. And the coming up with this summary quantity is basically the task of a skilled physicist. And then we try to estimate the distribution of the summary statistic, here are these like histograms, using just something simple like a histogram. So if we look at this picture of this collision that I showed you earlier which was a candidate for the Higgs boson, we have this very high dimensional data. What does the process look like that we take this high dimensional data and we distill it into a single number? Well, the first part we kind of take for granted, like you can see in the picture, there are these, for instance, these 4 red lines. if you ask a particle physicist, they'll say, oh, these are 4 muons that were reconstructed from the particular signals that they leave inside of the detector, because muons have this interesting property that they can, punch their way all the way through, all of this material. There's like several meters of lead and iron and et cetera. So they can go all the way through that, but they ionize on their way out, and that leaves a little trace of energy deposits along the way. And so we can see those energy deposits, and then we can identify them and then say, yes, we think there was a muon here. We can say if it was a positive or negatively charged one. We can estimate its energy and its direction. And then that's basically all there is to say about that muon. And so then in this example, we have 4 of them. So we don't, there's already lots of philosophical questions here about like, how do you know that that's a muon? You don't really see the muon, you see the energy deposits in the detector. But this concept of a muon has served physicists very well. We see muons in all sorts of different experiments, and we can predict what they're going to look like, and that's exactly what we see in the data. So physicists generally believe that the idea of muons are real, right? So if I take these 4 muons, that's great. Maybe I can sort of see them in my detector. But what about the Higgs? Well, if I produced a Higgs in this collision, it would have decayed instantaneously and never even made it to the next atom over before it decayed. So we're never going to see the Higgs boson in our detector directly. How do we know if we made a Higgs? Well, we want to try to somehow basically sequentially invert the causal process of how the data came to be. So first I identified these muons, and now we want to think about, okay, well, where did the muons come from? And then we're going to exploit things that we know, like relativity. So maybe you're familiar with E equals mc squared. That's not really what Einstein said. That only kind of works if nothing's moving. If something's moving, then you can sort of square both sides and add an extra component that has to do with the momentum. So you say the energy is related to the mass and the momentum through this equation. But I don't see the Higgs particle. So how do I use this equation? Well, you can take advantage of energy and momentum conservation. So if there was a Higgs that was produced, the energy that it had was kind of like the energy beforehand turns into the energy after, which is the energy that I would have in those 4 muons. And similarly, the momentum for the Higgs is the momentum before turns into the momentum after, turns into the sum of the momentum in those 4 muons. So I can take this equation and put them together and rearrange it. And basically, if I'm producing Higgs bosons and the Higgs bosons have a well-defined mass, then this particular combination of things should basically always give me the same number up to like measurement uncertainties. So let's see what it looks like in the data. That's this quantity that I just told you. For every collision, I calculate that equation I just showed you, and I get a particular number, and I histogram it. And then I can do that with both real data, those are the black dots, and then I can do it with simulated data. So if I take the simulation of what I expect from normal processes that I already know about in particle physics, I expect the blue histogram that's sort of sitting on top of this green histogram. And that's basically plays the role of our null hypothesis. That's what we expect to see if there is no Higgs particle. And these are the little Feynman diagrams that correspond to those processes. But if I'm producing the Higgs, I expect to see something else. I have a new process, and so I expect to see a bump sitting on top of it. And so that's the prediction. And you see there's this very sharp feature in the data, this very sharp bump. And the fact that it's a sharp feature is important. And the reason that, the way that I was able to use my domain knowledge to take the very complicated from the LHC data and come up with this very sharp feature is like a testament to what, physicists, are good at, right? So, and so as you can already see, the data look like they prefer a bump. And as we collected more and more data, the evidence for the bump became very obvious. And that is basically the experimental signature that we found the Higgs. But we didn't just do that in the one example that I showed you, this one. We did it across literally hundreds of different ways that you might expect to see the Higgs particle in the LHC data. And they're all related to each other. And this is where this collaborative statistical modeling framework that Priya alluded to, came into play. And this is just a graph of the computer, like the computer program that we use to calculate the probability of the data given the parameters. It's pretty complicated, but it's really like classical statistics. And the fact that we're able to relate all of these different kinds of parts of the data is, again, like shows the strength of the fact that our theory has this causal nature that allows us to relate all of these different parts of the data together. So then we analyzed this, and unsurprisingly, we found the Higgs, and we claimed the discovery. So I showed you this picture before, the slide previously, so that we took the high dimensional data and we boiled it down into the summary statistic. And this has worked pretty well. So this is an example of simulation-based inference, where this histogram, the red histogram, is basically playing the role, it's approximating the probability of the data given the theory, and I can calculate that from simulations. The problem with this approach, though, is it does not work well if you don't have a really good summary statistic. And if you want to, for instance, work with more like the raw data, or your summary is like a higher dimensional thing, then this approach is not going to scale. Basically, you're never going to have enough simulated data to make a high dimensional histogram. And that's related to this thing called the curse of dimensionality. So that's a bit of a problem. And so the interesting thing that's happening right now, which is using machine learning in some sense in a very traditional way, is since you can use your simulator to produce a lot of synthetic data, it's a very good match for machine learning. And what people have figured out how to do, and I've made some contributions here myself, is figure out how can we use the simulated data and then the value of the parameters that we know because we use them when we ran the simulator, to try to get a neural network or something else, some other kind of machine learning model, to effectively approximate the likelihood or the likelihood ratio or the posterior, one of these statistical objects that we need for doing inference. And basically, it's just a way of getting around this intractable integral that I referred to earlier. And so in that sense, it's very practical, but it's also very profound because it's giving us really superpowers across all sorts of different areas of science. And it's happening right now. And I think it's a very important, profound moment in the evolution of statistics. Previously, there were really big jumps that happened in statistics when you went from having to solve problems with just pencil and paper and using calculus, to where you could, for instance, if you didn't know how to find the minimum or maximum of a function, you could use a numerical optimizer. Or if you didn't know how to integrate something, with a pencil and paper, you could use numerical integration, techniques. Now we're at the point where the likelihood function itself is not tractable, and we're able to use machine learning to basically fill in that gap and give us a good approximation of the likelihood, which then allows us to go back and do kind of classical statistical inference. So this is a really important point, and it's allowing scientists of various stripes to be able to work kind of directly with the low-level raw data, maybe not have some good insight about what is a good summary, but you're not throwing away your expert knowledge. Your expert knowledge is in the simulator, and you're using machine learning as a way of basically transferring the expert knowledge from the simulator onto the surrogate, which is some sort of neural network or something. And so it's, again, I'd say it's all very practical, but it has, profound implications. Okay, so so if I step back a little bit and say, think about what's going on, as I mentioned before, there are all these areas of science that have these well-motivated mechanistic models that are their simulators. Machine learning is basically providing an ability to effectively bridge the gap between some low-level microscopic phenomena that interact in some way that's intractable to some effective statistical model for some higher-level quantities, some other higher-level phenomena. And so it's kind of more like a emergent phenomena, and you're able to bridge those two in some effective way. And so I think that if you want to be able to do this reliably, there's a question of how much simulated data do you need? And this is where, sometimes if you don't have a smart way of doing it, this is where it's going to require an enormous amount of simulated data, and this whole approach is doomed to failure. But if there is something that makes this work, then that's important. And that part of the secret sauce here is essentially causality. And this is where I think it connects to what James Woodward referred to as the more normative aspects about relating causality and causal inference. Okay, so I'm looking at the time here. I realize I'm going slower than I had intended, hopefully for the benefit of clarity. But but okay, so I'm going to switch a little bit, and don't be alarmed if I kind of skip over a few slides. So, okay, so what I just talked about was sort of one part of kind of the bigger scientific method. This is one of these kind of toy, drawings of the scientific method, which is, I don't really believe the scientific method has a flowchart associated to it, but if there is one, I prefer this one compared to the other ones that I find with a Google search. But the thing that I wanted to focus on here is that this part about gathering data and testing predictions, that's essentially the part that I was just describing. We're using machine learning to enable statistical inference, essentially for doing hypothesis testing. Okay, and so so you can either see it testing predictions, or maybe it's about rejecting a hypothesis. So it's kind of isolated to this part of this flowchart. Nowhere in there is there a part that's about thinking of interesting questions, formulating hypotheses, developing testable predictions, trying to figure out what experiment should you do. All of those parts of the scientific method are not reflected in what I just described at all. So if you want to try to incorporate them, what is that going to look like, right? So here is where you kind of start to connect to other ideas in machine learning that are more closely related to what's called like reinforcement learning. So maybe you're aware of the news that happened. Surprisingly, this was 6 years ago today. March 9th, 2016 is when one of these AlphaGo, one of these reinforcement learning deep neural network type approaches was able to beat Lucidol and a game of Go. And if you think about what's happening, there's an iterative type of interaction between sort of the AI agent in some environment, which is like the opponent and the Go board, and the AI agent is trying to decide what move to make next. And this looks a little bit like, here in reinforcement learning, you have an agent, it takes some action, interacts with the environment, and then there's some sort of updated state, and maybe the agent gets a reward, which would be something like, are they in a better position on the board or not? But this looks a lot like, for instance, a scientist, if that your scientist is the agent, trying to decide what experiment should I perform next. And then when they actually decide that, they interact with the environment, which is actually like performing the experiment, gathering data. Then the interpreter is basically the statistical analysis, and the updated state is essentially, for instance, like the Bayesian update from your prior knowledge to your posterior belief, right? And so this is kind of a nice like schematic of what experimentation looks like that connects with machine learning. And this can all be formalized. I'm not going to go through this, but this is formalizing it in the language of statistical decision theory. You see things like states of nature, types of observations, what kind of actions you want to take. And again, you see these normative concepts like loss functions and risk and all of these kinds of things. And then you can basically, evaluate how well a particular strategy is working or not. So if you wanted to design a new experiment, you might say that like the thing that I'm going to use to decide which experiment to perform next, or which intervention I want to perform, is the one that is going, in expectation, is going to move me from my, prior degree of belief to a posterior degree of belief where the information gain is maximized. And you can formalize all of that in these equations, not so important. But I should say what is important is the way that the fact that you're able to answer this question, like what do I expect would happen if I do a certain intervention, the only way you can answer a question like that is if you have a causal model. And so because the simulator is a causal model, I can actually answer this question. And then if you look the different quantities that pop up in here, priors and posteriors, if you have a simulator, then you get back into the situation where the likelihood is intractable, but you can take advantage of these simulation-based inference things to try to incorporate the two and do experimental design. So here's a bit of a flow chart. If I want to do experimental design, where I'm sort of trying to optimize the expected information gain of my next experiment, I sort of do an experiment, I get some data, I use Bayes' theorem to update my prior to a posterior, and then I want to optimize what's my next experiment going to look like. So that's some loop that I do. And what does it look like? You can go through it, but basically now you sort of do the same thing that's on the left, but with simulated data that you expect, that you would see if you do a certain intervention, which you can calculate because you have a simulator. But this becomes, it's just very, very expensive computationally to do this because you have all this simulations inside of loops. And so computationally, this is just, it's doable, but it's very, very expensive. Now, I prototyped this with some colleagues, and we were able to get a system that could basically optimize, what beam energy should you use for a particle collider if you want to measure one of the particular quantities inside of, the standard model called the weak mixing angle or the Weinberg angle. And you can do that. And it basically says, okay, the expected information gain as a function of the center mass energy looks something like this. And this agrees with what you expect if you're if you've got a PhD in particle physics. This is probably some problem that you had to do for homework at some point. But what's interesting is a graduate student can look at the equations and can just reason through it without any of this computation and say, yes, you should run, like at roughly this energy. That's where you're going to learn the most. And that's exactly what the experimentalists did, right? So it's cool that you can operationalize this whole thing with machine learning, but it's very inefficient. And somehow humans have been able to do this much more efficiently. So after I put this together, I tweeted about it. Danilo Rezende, who's a well-known machine learning researcher, was like, "Oh, that's cool. You've got the whole scientific method in a Python notebook," and it's half true, but it's really in the most confined, pristine case possible. The simulator is well specified. The space of experimental configurations is very well specified, and still it was hard to do. So I guess what I would draw attention to is if you want to be able to do something like this and like humans do in a open world of possible experimental configurations, and you also want to include hypothesis generation and things like this, modern AI is very far away from being able to do that. But that's interesting, right? Like that's the path that we want to go down. Okay, so going back to this kind of overall big picture about the scientific method, I think if we want to get to this point where we have AI type systems that are actually designing experiments, formulating hypotheses, we're missing some, it's not going to be some end-to-end learning deep neural network that has no structure. It's going to, I think, need to have components that you can point to that are organized in some way that looks like some kind of causal structure. And it may not have the same kind of ontology that current physicists have. It may be some foreign ontology, but I think it's going to need to have some ontology of different kinds of components that's at its essence causal, and that it's going to need to be able to manipulate them, effectively, if it's going to do, science in any kind of reasonable way. And I think thinking through that is really important for us trying to put our finger on what is it about causality that's important, and to what degree are we should we expect that this future AI system is going to arrive at an ontology that sort of maps one-to-one onto the ontology that physicists have with electrons and muons and Higgs bosons and things like that. Maybe not, but it would be it would be a little bit surprising, I would say, if there wasn't some correspondence there. Okay, so so this was just a kind of an editorial note that, if you think about how humans do this, it's pretty amazing. And when I think, when I introspect onto myself as a physicist, I definitely have roughly 5 or so different mental models for experimental particle physics that I, bounce between at different scales. And I choose the one, that's appropriate for a given task. And that's how I do physical reasoning. And I have a very hard time seeing how something that's only working at the low level of a simulator, with tracking the microscopic trajectories of particles ionizing off of atoms is going to be able to cope with the kinds of problems that a human does that can just quickly jump to a very stick figure picture of what's going on. And I think that AI models are going to need to get to that point. So in my last couple of minutes, I'm just going to flash a few things that are a view from the machine learning and AI community to basically try to say that this line of thinking is not foreign to the AI and machine learning community, which to some degree I'm a part of myself now. But just some concepts that are floating around in that discussion. So one of them, there's something called the no free lunch theorem, which basically says that if you don't make any assumptions and you imagine all the possible machine learning problems that you might have, all the possible data distributions, that essentially there is no, every algorithm is going to perform equally well to every other algorithm on average. So if one algorithm is doing better than another, it somehow has to be leveraging something that's, atypical. And so if you think about, say, images, if you don't add any structure, something on the left here, that's the typical image, it's just some random noise, right? That's what most images look like that. But natural images don't look like that at all. They have all sorts of structure and smoothness and all sorts of things going on. And it's so the effectiveness of convolutional neural networks and things has something to do with the fact that they're exploiting the structure that's of actual natural images. And otherwise, things like cursive dimensionality, you would naively think that it should basically never work. Stefan Mallat is a well-known researcher, did work with wavelets and things like that. So he's talking about learning physics with deep neural networks, and points to two really central pillars if you want to hope that this is going to work. And one of them is finding symmetries, and the other one is separating phenomena at different scales. So we've already seen that a few different times, and the convolutional neural networks, they incorporate both of these ideas. The broader, class of these types of ways of adding something to the model so that it will work are referred to as inductive bias. It's biased in the sense that it's biasing to be effective towards data of a certain type, that has certain characteristics, and it's maybe not going to help in other situations. So here you see scale separation, symmetry, the idea of compositionality, the idea of relationships between different objects, and causality. These are, I think, some of the most important forms of inductive bias. You see Peter Battaglia, who's at DeepMind now and was previously with Josh Tenenbaum and company, and has a background in human and cognitive science, talking about model building, combinatorial generalization, sort of the infinite use of finite means, and about these kinds of ideas about intelligence and model building. He's taken these ideas to do really impressive work that have to do with you're interested in studying some physical system, and you're going to come up with a neural network architecture that has some structure associated to it that's kind of a mirror of what you think the actual physical system looks like. I've worked with him on some of these projects. I think it's a very promising direction. And then you see Stephanie, who's at MIT, talking about a more formal version of the same idea. She calls it algorithmic alignment, and she has some formal theorems and things, but it's some approach to try to formalize this idea of inductive bias. Sorry about the street noise here. And then finally, this is Yashua Bengio talking about, okay, dear machine learning community, what if we had the right causal structure in our neural networks? And the claim is that basically, if you have these kind of independent mechanisms in your causal, mechanism, that you'll be able to learn with many fewer samples. That's referred to as sample complexity, and that'll be more robust to things like what's called distribution shift or domain shift and things like this. The idea that if the data that you use for training is not exactly the same as the data that you're trying to apply it to in the real world, it'll be more robust. And you see various discussion from other luminaries in machine learning. So these are very much on people's mind. These topics are very much on people's mind. And what I'm interested in is the fact that the kind of traditional direction that's coming from physics and this kind of modern machine learning thinking is coming together at the same time. And the role of causality is very important. So I already mentioned basically this idea of trying to, the importance of machine learning for simulation-based inference. But you also see this idea that if you can incorporate what you know about the data generating process into the machine learning models themselves, that can basically help with sample complexity. And it's kind of a path towards how AI might actually start to learn the underlying causal mechanism, which I think is on the path towards AI generating hypotheses and designing experiments. And then lastly, I'd just say that there's, going back to some of John Woodward's points, is that this way of framing it and thinking about it allows you to basically do experiments where the simulators basically, they have a ground truth data generating process where you're not arguing about what the actual causal story is, because it's right there in front of you in your computer program. And then you can look to see what kind of, how effective is it to impose this type of inductive bias on the model, and how much does that help in terms of these normative aspects about that bring together causation and causal reasoning. And with that, I will say thank you and remind you that next week on Wednesday at 4 p.m., I have a follow-up discussion with Zena, and I'm looking forward to that very much. Thank you very much.
Thank you so much, Kyle, for that absolutely fantastic talk. Very, very clear exposition, and I really appreciate the fact that you put effort into combining and putting together the various threads that previous speakers and the directions that previous speakers in the series have taken to address these issues. I personally really appreciated your showing the differences in the meaning of causality, the different meanings of causality that have been used and how they actually relate to each other. So there are questions lining up in the chat, but I'm jumping with one question myself, so I'm going to take this chance to ask you first, which is, so I loved your sort of clarifying the process of inference and how in a domain like physics, the known laws actually guide us and how replicating that. So I was wondering, so in terms of new discoveries, right? So suppose there's a hitherto unknown conservation law. And because of the, because we are using our domain knowledge to come up with a suitable summary statistic, and, just following the language of the examples that we use in physics, right? So is it completely impossible because our summary statistic is limited because it's defined entirely by what is known, prior knowledge, that something that is hitherto unknown will actually be missed? Like, how would you capture? I want to understand how you could open up discovery space.
Yeah, no, that's a great question. So I think, the typical way that we've gone about designing summary statistics has been guided by how we think the data, our assumptions about what's actually going on, or there's a hypothesis, we don't know if it's true or not, but if it were true, it has the following consequences, and we can use that as a guide for designing a summary that's going to be very powerful, right? But there are other approaches that you can use to kind of take it's essentially like data compression. You have high dimensional data and you're going to distill it down to some lower dimensional thing, and you'll discard some information on the way. That's fine. I mean, these summary statistics that we use in particle physics are good for one task, but they're not good for other tasks. So it's not surprising that you're going to throw away a lot of data. But there are certainly approaches where you try to sort of learn. In machine learning, they would be referred to as a representation of the data. You have the full data, and then you have some representation that will capture some pieces of information, but not others, right? And so there are all sorts of approaches, including unsupervised learning, or even what I was talking about and what I showed with where we're using neural network, that neural network surrogate in some sense is a learned summary statistic. But it's learned because it's targeting a specific hypothesis. If you wanted to do it in a way that's like what I think the essence of your question, where you're not assuming the hypothesis, but you're trying to learn from data, what would that look like? And there certainly are various approaches that are coming out now, things that are related to like anomaly detection and stuff like that, where you try to essentially learn some representation, which is good at capturing what most of the data looks like, and then you look for something unusual and some sense of unusual. There's progress there, but it's a bit of a can of worms. If you wanted to discover something like a symmetry, I think there definitely works there to try to, how could you discover them? One of them is you basically sort of enumerate a bunch of possibilities, and then you basically
you brute force it, but you have to still start with some prior expectation. Maybe it's even as silly as dimensional analysis or something, right? But you have to just brute force through possibilities. That's pretty clear. So hey, let me move on to the first question, which is somewhat related. It's from Fedros. What if we want to look at physics beyond the standard model, where the theory is an uncharted territory, in a manner of speaking? So how do we hunt for these signatures?
Yeah, no, exactly. So I think it's a question that comes up a lot in this talk, which is like, that's great and all, but I want to learn something that's beyond my simulator, I want to learn new physics. So So one thing that's important to realize is that we don't just have a simulator for like the standard model. We have simulators for basically all of the crazy thoughts that theorists have come up with over the last decades. So we have a formalism that's kind of general purpose, and we describe essentially every new physics theory that we can think of gets described in that formalism, and the tools that we have then allow us to make predictions of what we would expect the data to look like for kind of any theory in that space of theories. Now you could say I want to go even beyond that and ask about theories that that are not expressed in that formalism, and then I guess what to say. Essentially, all kinds of inference are going to be done at some point in the context of a model, right? So you need some notion of saying, what do you think the data is going to look like? And that doesn't have to be expressed in the language of quantum field theory. It could be a very empirically motivated way, like signature based, where like, what if there's a bump in the data, or what if the data does this? It doesn't have to be based on quantum field theory or something. And so then you can say, well, I don't know exactly what the bump looks like, but can you search for any bump or any sharp feature, or does it ever have any kind of if you don't say add some other assumption, you just say anything other than the standard model, then you open yourself up to a bunch of possibilities that people don't want to take seriously, like electronic noise in your detector that has no kind of structure to it, that no physicist would look like and be like, ooh, new physics. They'd just be like, I've got a cable that's loose or something. But trying to figure out how to balance that between very well specified theories that are so narrow that they maybe seem uninteresting, and the completely open-ended could be anything where you have no power. Finding that trade-off is challenging. And so coming up with a way to describe theories in some kind of effective way that people are happy with, that maintains some power is kind of a transition that's happening. I mean, it's an old problem. It's a classic problem in statistics, but it's renewed. It has renewed energy in the context of machine learning now.
Thank you very much. The next question is from Li Hao Yan. In my understanding, the state-of-the-art machine learning algorithms really act like a black box. It's very difficult to interpret why the algorithm actually works. Would this reduce the power of ML inferences?
By keeping it a black box, or by making something that's not a black this meaning what I'm preferring?
Yeah.
Well, I think that, yeah, so let's see what to say. So, that general idea of adding structure to your architecture, your model, was referred to as inductive bias, right? So why is that term used? Well, inductive, because you're kind of adding some structure to the model to try to, because you're, but the bias part is because you're not saying as an equal playing field to all possible scenarios that the data could look like anything. You're saying, I think the data has some kind of, is organized in some way. It has some type of structure. And when you impose that, then you are kind of, you're favoring yourself in that direction. And so you're kind of biasing yourself in that way. Now, if reality actually has that structure, then you're fine. Like if the reality is there, if reality is not quite in that family of things, then maybe you have a bit of a problem. But generally, if you can impose that structure and it's like the right thing, you're good. And of course, you don't know if it's right or not. So it's a tough question to answer generally. But the other thing to say is, if you think about situations like, there have been papers, I referred to some of the work by Peter Battaglia and company, and there's a recent paper by Miles Cranmer, no relationship, who's looking at, for instance, planets moving around and trying to infer what is the gravitational law, and we've done some work like that. Those kinds of models, you can use what are called graph neural networks, where the nodes of the graph are things that have physical meaning, like planets or particles or atoms, and the edges between them have physical meaning, like force between two planets or something like that. And in that sense, you're kind of doing the hard work for the machine learning. Like, the machine learning algorithm didn't know what planets were, or that it wasn't some like linear combination of planets that should be a node. It said like each planet should be a node, and there should be a one-way bidirectional relationship that's symmetric and all sorts of things. And so you impose all that inductive bias, but in that problem, you think it's right. And if you do that, it just helps tremendously, right? If you take that away, you could, in principle, get there, but you're going to need a lot more data before you perform well.
Great, thank you. And there's, of course, a a really profound question from Brian. Thanks for this really fun and accessible talk, Kyle. Could you talk a little bit about what you've been thinking regarding the implications for epistemology and the limits of human knowledge or information acquisition?
Yeah, it's a good one. Yeah, I mean, I think, well, what to say? I'm not like a trained philosopher, so probably everything I will say will sound like, naive and etc. But I do often like to think of it in terms of, if some alien civilization came and landed, it would be clear that they are, if they have the fancy spaceships and stuff, it's clear they have advanced technology. You're not going to be arguing about if they're intelligent or not, and it's clear that they probably have some notion of science, or they probably wouldn't have gotten there, and so compared to other areas where you, like with AI, human level AI, where you're arguing about what does it mean to be intelligent, it's like this framing, you're kind of not. It's a very understandable notion for, I think, most people, that yes, they're intelligent, they've got some notion of science. And then you imagine starting some conversation with them. You don't have aligned language. It's not Star Trek, but say you can figure that part out. Then there's going to be a question of like, does the ontology that they have like align with the ontology that we have at all, or do they have like a totally different way of thinking about everything? How did that come to be? And I think that's it's an interesting question. It's not clear. And then when you then use that way of thinking about it with the conversation towards like robot scientists and AI, like, is there any expectation that some AI type thing, like, should it be interpretable to humans? Well, I don't know. As long as humans are in the process of designing experiments and doing hypothesis generation, it's pretty important that we can understand what happens for the current experiment that we're doing. And if we somehow seed that and have like really black box neural networks and things that maybe solve the problem we're on today really, really well, but if something goes wrong, we don't know what to do next, then the whole way in which we aggregate knowledge in the scientific enterprise up until then is going to be kind of dramatically affected, and I think that would probably not go well. But I do see, and you're already starting to see it in like self-driving labs for chemistry and stuff like that. You have kind of closed loop systems, usually only in pretty confined settings where that's effective. But yeah, I think it's a fascinating question. I don't know that I really answered it, but.
A sort of a related a thread that occurs to me from what you've said, Kyle, is that domain knowledge in many ways is traded off with the amount of data, right? So if you don't have domain knowledge, I mean, is it really true that having an infinite amount of data means that you don't actually need domain knowledge?
Oh yeah, so that's interesting. Well, one thing that I mentioned earlier, this like ladder of causation, and even if you have an infinite amount of data and you have like infinite computing power, you can basically, any probabilistic question that you want to answer, but that can be expressed as like a joint distribution or a marginal or something like that. You have access to all of that. You can do all sorts of things, but you can only answer questions in the lowest rung of the causal hierarchy. If you ever want to ask what would happen if I intervene, you're just not going to be able to answer that on principle. So so I don't think, that's why I don't think data, like this whole data-driven thing, is kind of like missing a pretty
right.
point.
I mean, this is where I was going, right? Because in our fields, for example, in astronomy, cosmology, particle physics, I mean, we are really hurtling towards the, just procuring huge amounts of data, somehow thinking that is going to be sort of the resolution in providing deeper insights into the theory, because there are limits. There are limits that.
Yeah, I mean, it generally helps, but yeah. At the LHC, people use this term data-driven analysis techniques a lot. What's interesting is if you look there, a lot of times what happens is that there's some clever insight about how you can reuse the data that has some characteristics and then sort of use it to extrapolate to what it would look like in a different setting. But the only way that you're able to do that is because we think, oh, well, if I take out the electron and replace it with a muon, then I have this following relationship, right. And you assume everything else is not unchanged and all sorts of stuff. So that looks a lot like causality, like right. All of those kinds of operations are kind of using causal structure. That physicists have learned to do this, and those are the
pre-existing knowledge of causal
yeah,
structures.
but,
right?
but we don't usually describe it in those language. We don't use the language of causal inference when we do it.
I think Sham has an urgent hand up. There are many more questions, but did you want to speak up, or I think you may have to type in the chat, Sham, because we are in the webinar format.
And also, Priya, we have, Zena has contributed something in the chat. I think because of his host privileges, he wasn't able to go into the Q&A.
Oh, I see.
I see the question. I don't know if
yeah,
you see
Zena,
it.
go ahead and ask. I think you can unmute yourself. Right?
I can maybe, well, we could just read it. So it says, a question, if I may. You mentioned that reality seems to be striated so that it can be understood at different levels of abstraction. Could it be instead that this is more about human minds than the world? And more pragmatically, do you have thoughts of model representation that could capture multiple different abstractions simultaneously? Yeah, that's a great question. Now, I mean, when you get into, I mean, this is a super philosophical question. I mean, there's a, there's a question like, to the extent there are cells and organs and, an individual, and then like a populations of some species, it's, to me, I guess I'm a bit of a realist there, and that striation seems to be pretty real. In a physics context, you can go between things like quarks to things like protons and neutrons to atoms, and it could be that that's all an illusion, but it's certainly a very effective description that has worked across wildly different kinds of experiments. So it's a very effective abstraction. And again, I'm certainly a bit of a realist there, but I'm open to the fact that it's the broader philosophical discussions there. But in a practical sense, whether those things are really real or not, the extent that humans, use them as a tool to make predictions about things has certainly empirically served us very well in navigating the world, and we have success after success after success in using those relationships to organize things. And I think individual humans, it certainly seems to me, I'm not a cognitive scientist, you read, well, what many cognitive scientists are saying is that this does seem to be how we're organizing the world, and that our success as a species has a lot to do with being able to kind of pick the appropriate abstraction and do reasoning very efficiently using it. I think then the last part of your question to me is the part that's the most compelling currently is, how do we build that into some kind of AI machine learning like architecture? I think in the context of, step one is, how do you do the first, even before I've like different layers at one particular layer, how do you encode that bias? And I think that's where you see things like graph neural networks, for certain things where you can really point to individual things like planets and stuff like that. It's very clear how to do it, and it works really well. A research direction that I think is interesting is like, what if you didn't do that by hand? How hard would it be to, like, if you took the data and reorganized it in some way, and then you said, okay, you want some meta machine learning algorithm to figure out like what are the objects in your ontology to attach to nodes in a graph and what the edges mean, and how you would do that in some more automated way. That's interesting. There's work that's going on about dynamically building graph neural networks, which is in that direction. And then there's the idea of, if you have a graph, like coarse graining it so that you have, and that looks, it looks sort of like the pooling operations you see in a convolutional neural network. So there are certainly ideas, and there are people exploring that. And I have, trying to do some work like that on my own. And I think it's, that's super interesting. And, there are various people playing around in that area right now.
Yeah, no, I mean, Zana, this is something we hope to talk more about during your presentation on next Wednesday. But Kyle, related to this, I have this little aside related, which is, I mean, isn't it true that when we are coarse graining a system in physics, for example, it's very intentional, right? I mean, we are coarse graining because we know that at a certain level of abstraction, we will have additional information that we can use, additional priors that can play into, we know a new set of rules, a new distribution, a form for a distribution, Maxwellian, that will work for the ensemble, right? So the coarse graining is always because we do already have prior information about how a system will look when we.
I would say, yes and no. I think that I would say that if you look at major advances in science, a lot of times it's like the fact that you're able to first identify, here is a scale where there is an effect, there is going to be a useful description, and there's going to be some kind of laws that describe what's going on. And then you need to kind of have some ontology of what are the right degrees of freedom or the right kinds of objects to even talk about at that scale. And then what do their interactions look like? And then, what are the laws that describe that scale? And that sometimes that just happens kind of on its own, at that level. But when those things happen, they're really important, right? Those are like major events in science, right?
Yeah.
And then and then in the reductionist type picture, if you can then tie it back to the lower level scale and say, this is how they're related, that's another, these are all Nobel Prize type events. And so part of what I think is so profound about the simulation-based inference thing is that you start off, it's kind of allows you a way to maybe bootstrap that process. You start with the simulator at one scale, what's going on. Then there are some emergent phenomena that are really complicated and you don't know what they are, but through learning, you're able to find kind of what are the right summaries, coarse graining, whatever, that kind of identify the new degrees of freedom.
Right.
You don't have a name for them yet, but they're the new kind of effective degrees of freedom at that coarse grain scale. And then if you can just end up learning laws on those new, coarse grain degrees of freedom, then you can lift up and operate very, very quickly. Right. Compared to the,
it almost sounds like, this is a completely alternative. It's not quite a demystification of the standard process of discovery, but almost a brand new way for discovery. At least it feels that way, right?
Yeah, it just seems like there's potentially a path to kind of systematically hop between, or maybe you already know the right scale for whatever reason, but you don't know how they're related.
Right.
And you can simulate, and so they're definitely, we have some work going on that's basically trying to do exactly that. I know how to simulate at one scale. I know there's a phenomena emerge at a different scale, so I can predict them. And if it doesn't require exponential amount of computing time, then I can get enough data where I can try to learn that relationship. And that's really compelling, I think.
Thanks. So Jeremy Zucker has the next question. What do you recommend as the best Python library for performing simulation-based inference?
So good question.
Something else? Are there any probabilistic programming languages that can do simulation-based inference?
Yeah, I can give a quick guide to this without getting too in the weeds. So there's a tool called SBI, which stands for simulation-based inference. It's kind of like a nice general purpose Python wrapper type of approach. So you have a way to kind of interface whatever simulator you have to it. Generates data, does the machine learning components, and then you can do inference. And it implements several different techniques.
Right.
So Elfie is kind of is more tied to one specific technique, and so which is fine, but it's sort of less of a toolkit in general. And then you mentioned Ada Loomis. So that was a project that I was involved in. So there's a kind of important distinction there, which I didn't get into. But if you remember this diagram that I drew, that sort of had parameters on the on the left, data on the right, and in the middle there were latent variables. What the Ada Loomis and PyProb, this probabilistic programming approach, it doesn't try to sort of bypass the latent variables and go straight to the parameters. It actually gives you the capability to do inference on the latent variables itself. But that's a much harder problem. It's a much more complicated thing to try to infer. So if you want to try to do that, that's the tool for you. Just know that it's a lot harder. So in that Ada Loomis work, we use supercomputers and stuff like that. In other contexts, that's not required, but kind of depends on your problem.
Great, thank you. So I guess his next question is Shyam Sundar's. How much of this can be extended to study of social phenomena?
Yeah, it's a good question. I think, I had this discussion once before with like, you know, a lot of the way that the simulation-based inference stuff is set up, you need to be able to generate data conditioned on or given some, I said parameter, but it could be given some whatever you want. So you could, for instance, look at the text of tweets given a certain hashtag, you know, and that could be like a political hashtag, or it could be, you know, the use of some emoji, or, you know, something like, you know, your favorite sports team or something like that, right? So, so it doesn't actually have to be a simulator. You just need a data generating process that you can condition on. And so that makes it interesting because you have the opportunity to realize what I was talking about when you have real world data generation process. So also, like, for instance, I showed this toy, you know, I can just generate data from this toy over and over and over. It doesn't have to be a simulator. You know, I can use the actual physical system to generate the data and use all the same methodology that I described. So I think there's a, you know, there's an opportunity to use that in all sorts of different like social contexts and things like that. Obviously, if you're going to go down that road, you should take a moment to think about the ethics of what you're doing and all of the things. You know, those are important considerations. But in terms of the methodology itself, there's certainly opportunities.
Great, thank you very much. So the next question is from Michael Churchill. For simulation-based inference, what are the prospects for working with very, very expensive simulators like exascale computing?
Yeah, so that's also a really good question. So in the context of Large Hadron Collider, you know, the real collisions are happening about 40 million times a second, but to simulate one collision takes about 10 minutes. So there's like an enormous, you know, gap between how long, but 10 minutes doesn't sound that bad, and you can run it on a fairly normal computer, and we have a lot of computers. So it's expensive, but it's doable. If you wanted to go into a situation like, for instance, you look at the waveforms that come inside of the LIGO, the gravitational wave detector, and you want to predict what those waveforms look like given some black hole, you know, merger. That simulation, you know, at one point requires numerical relativity and all sorts of stuff, then there's, you know, other phases where you can do that faster, but it's still pretty expensive. And that's to simulate the waveform for like one scenario. And now you want to scan through this fairly high dimensional space that describes the different ways the black holes might be oriented and their mass and spin and all these things. So that becomes expensive. And but actually, if you wanted to try to do normal like Bayesian inference in that setting, it's really, really, really expensive. So people have started using likelihood-free inference techniques or simulation-based inference techniques basically to make that faster. And so what's nice is that you now have situations you pay an upfront training cost, but once you're done with that, you have what's called an amortized setup where you can do inference very quickly. So now there's systems where they can look at the waveforms and within microseconds tell you what the posterior distribution on the sky is, so that you can slew your
Right.
Telescopes. But there's definitely a lot of ongoing work about.
Yeah, but that, you know, but Kyle, in that case, the training set is finite and limited, right? So there's a limited set of waveforms that are real gravitational waves, right? Or you think that when you refer to the training set, do you mean like the full set of all possible wave patterns,
or like the ones that you would get from, like, say, running a simulation?
GR simulation. Yeah, GR simulation.
With whatever approximations or things you want to stick in your simulator. You know, I don't want to get into the weeds of like post-Newtonian stuff, but like but the what was I going to say? The other thing there is that there's a lot of work going on, which is at the beginning, say, like for that example, you don't know where on the sky, and you don't know, like, have any idea what the mass of the black holes were, but you could make a very rough scan at first and start to get an idea, and then refine with more simulations in the relevant region. And so you have this kind of iterative approach that uses this buzzword of kind of active learning. And so there are techniques that do simulation-based inference where there's like an active learning loop on the top to try to make the simulation as efficient as possible.
Because I mean, these are cases where doing, having a library would be too onerous, would be too computationally expensive.
Yeah, trying to do it upfront is like, not great. And earlier there's a question about software. This SBI tool, for instance, implements these active learning techniques, but there's some others as well. Yeah. There's one called Swift, which is pretty nice.
Let me see if there are, I think there's one more question. It's Jeremy Zucker again. If your simulator is differentiable, what methods exist to speed up simulation-based inference?
Yeah, that's a great question. So, I mean, without trying to give a shameless plug or something, we wrote a review article about simulation-based inference techniques, which maybe
it's a great article, by the way. I can plug it. It was in PNAS, and I think it got me started thinking about these issues.
Yeah, but it was meant to be fairly accessible. But one of the things that we spent some time there is saying, you know, if you can open up your simulator, open up the black box, and either instrument it with probabilistic programming type of skills, or if it's differentiable, there's different ways it can be differentiable. It can be differentiable in the sense of like input-output relationships, or it can be differentiable in the sense of the probability of this run of the simulator, like what's the derivative of that probability with respect to the parameters of the simulator. So there are different kinds of derivatives that you can take, and if you can you can take advantage of them, and it can lead to dramatically more efficient learning. So we have a paper called mining gold, which talks about one type of derivative, and there we show that for several problems that we were looking at, we could reduce the simulation budget by like 3 orders of magnitude. So so if you can take those derivatives, things that were taking millions and tens of millions of simulations turned into like 1,000. So that's a pretty big difference.
Great. Thanks very much. Are there any other questions? I'll just give everyone another minute if they want to type something up or type up. If not, I mean, to be continued. I really look forward to the conversation between you and Zena next Wednesday. Meanwhile, thanks, Kyle, for this wonderful talk, really clear talk, explaining simulation-based inference to us, and looking forward to seeing you on Wednesday. Thanks,
Great,
everyone.
Thank you very much.
Yeah. Thanks, everyone. I also want to say, give a big thanks to Ty and to Guy Ortoliva for helping with the logistics and organizing this talk and series. Bye, everyone, and see you next Wednesday.